This video is going to talk about dependent and independent variables. So we have a graph here that represents the cost of parking a car in a car lot. Taking a look at this graph, how much would it cost to leave the car in the lot for 1 hour? Well, if I look at the number of hours down here and I trace it up, I can see that it's going to cost $5. What about for 2 hours? How long will it cost for 2 hours? Well, go down to 2, see where it lines up, and it turns out that that's going to cost $7. What about for half an hour? Well, I'm going to go down here, I'm going to trace this line up, and I'm going to see that halfway it's going to be $4. How much would we pay before entering the lot, even before parking the car? We can see that there's going to be $3 just to pull in the lot. You're not getting charged for how much time you were there. It's $3 to start, and then each additional hour is going to cost, well, this goes up by 2, this goes up by 2. Let's go ahead and put a little divider there, and then the next hour goes up by 2. So it's going to increase by 2 hours, by $2 per hour. This changes because after 3 hours, you're just paying $9 total. So the rule would be enter the parking lot for $3, pay $2 each hour until you get to that third hour, and then the charge stops and you've reached your maximum of $9. A different parking lot charges $2.50 per hour, flat, just $2.50 per hour. So the mathematical rule for the cost of parking there would be $2.50 times the number of hours, or the time that you're there. So they want us to write ordered pairs for the time and the cost of the second lot. So 1 hour would be, well, excuse me, I went to go put a dollar sign there, 2.5. So let's rewrite that. 1 hour would be $2.5. So 1 hour, $2.5. Come on, buddy. 0 hours would just be $0. Doesn't cost you anything for that. 2 hours means you're going to get charged $2.50, which is $5. So we're going to go up to 5 here. 3 hours means we're going to add another $2.50 there. So that's going to be $7.5. 4 hours means another $2.50. That makes $10. And we would keep going. You can see that there are some times that it's going to be cheaper to park in that second lot. If I'm going to park for less than 3 hours or less than 3.5 hours, I'm going to park in that lot number 2. But if I'm going to park for 4 hours, I'm going to want to park in the lot number 1, the one that maxes out there. So it's something to pay attention to as these numbers keep climbing. They want us to write the equation for the second parking lot using the variables C for cost and T for time. So what we want to know is what variable in this equation is the input. Well, the input is that first number because it's an input-output table. What you get in and then what you get out from it. So we put in 0 hours, we get out a cost of 0. We put in 1 hour, we get out a cost of $2.50. 2 hours, $5. 3 hours, $7.50. 4 hours, $10. So we see that the cost is going to equal the number of, well, I'm sorry, T, not H. cost is going to equal $2.50, or 2.5 times T, times the amount of time that you're in there. You can park in the lot for any number of hours you want, but the cost depends on the duration of the park time. So C changes depending on T. Mathematicians name the input the dependent variable and the output the independent variable. In this example, the dependent variable is T and the independent variable is C. Let's talk about a boat that leaves port at 9 o'clock in the morning. It travels at a steady speed. Sometime later, and you can see the boat traveling at a steady speed right here, sometime later a man jumps into the water and starts swimming the same direction as the boat. Okay, we can see that sometime later on the chart is represented by 15 minutes later. How many minutes passed between the time the boat left port and the time the man jumped into the water? When did the man jump into the water? Well, he's going to jump in right about here, because this is when he started swimming in the same direction as the boat. How far from the port was the man at 9:15 a.m.? Well, remember that the boat left port at 9 o'clock. So at 9:15, 15 minutes after 9 o'clock, the man was 3 kilometers from port. How far from the port was the man? Oh, I'm sorry. That's down here. When did the boat overtake the man? When did the boat catch up to the man? Well, that's going to be 60 minutes after 9 o'clock, or at 10 o'clock. How far did the boat travel in 1 hour? Well, in 1 hour, going from 0 to 60, the boat traveled 6 kilometers. Then we want to know, how long did it take the man to swim 1 kilometer? Well, we see 1 kilometer, or 3 kilometers here and 4 kilometers here. And that ends up being 15 minutes on our chart. How far did the man swim before he was taken aboard the boat? Well, he started off at 3 and he got all the way to 6. So that's 3 kilometers. And we can see on the graph where the man was picked up by the boat, because for a while, neither one of them made progress, probably as the man was climbing up on there and making sure that he didn't get accidentally run over, because that can be dangerous. Be careful, be safe, ladies and gentlemen. Did the boat continue traveling when it met the man, or did it stay in the same place for a time? That's again that same thing that we're talking about right here, where things are stagnant at that 6 kilometers for this 15-minute time. And then we see that the boat docked at another port 9 kilometers from the starting point. At what time did this happen? Well, I see this 9 o'clock right here. To know what time it happened, that happened 105 minutes after 9 o'clock. How long is 105 minutes? Well, I know that 60 minutes is 1 hour. That's 10 o'clock. And if we're going in 15-minute increments, that's 10:15, 10:30. That ends up being 10:45. Have an absolutely swimming day.